All right. Hi, folks. We're just going to give everybody one more minute to filter in, and then we're going to be getting started shortly. Okay, so it looks like we are ready to go. Just want to say welcome to everybody. We're really excited to have you on today's Tech Talk, Modeling and Solving Optimization Problems with Decision Diagrams. My name is Dawn, and I'm part of the NextMove marketing team. I will be helping to support the webinar today. We're slated for 30 minutes and we have a lot of content to get through. So let's get started. And with that, Ryan, I will turn things over to you.
Thanks, Don. And thank you everyone for attending. This is one of my favorite topics, so I'll try not to go over, but I apologize in advance if I do. I'm Ryan, the CTO here at NextMove, and today we're going to be talking about decision diagrams. If you're new to decision diagrams, which probably many people are, this is basically going to be a talk about what they are, how did they arrive on the space, what do they do, how do I use them, and how are they different or similar to other optimization technologies. We won't really be talking about things like benchmarks and computational results or stuff like that. We won't be really showing any code. This is a talk about how do I model problems using decision diagrams and where do they fit into the optimization space. So decision diagrams are kind of the new kid on the block. And in order to understand what they are, I think it's important to go back to the beginning of time. And so for optimization, that really takes us back to the 1940s. If you've taken a class in linear programming or mixed integer programming, you are no doubt familiar with the name George B. Dantzig and a little bit about how optimization started, or at least linear programming started in that time period. Back then, we collectively were really good at solving matrices, right? And so when people who were doing early optimization realized that we could use math to solve what are essentially choice problems. I've got a bunch of things I can do. Which thing should I do? It was very natural for them to take the matrix as the underlying vehicle and matrix algorithms and use that as a starting point to build optimization on top of. And this really sort of is still the case, right? When we study optimization, when we're coming to it as students, the way that we learn is by doing, say, simplex tableaus and learning the reduced simplex algorithm. We're doing matrix operations to try and solve choice problems. And this is very natural and good and has a lot of good characteristics. A byproduct of this, though, is that to study operations research and to study in particular things like linear programming, we end up being, in essence, translators. Our job as an operations research analyst is in part to understand a solver and to know the solver in and out and to be able to take operational or real world constraints or aspects and translate those into something that the solver understands, right? And so there's nothing inherent to a matrix representation of a problem or a different representation of a problem that can represent things like precedence constraints or choice constraints in the real world. Those are things that we as modelers have to understand how to communicate to the solver. And so that's the part of the art of programming or linear programming is this communication between the solver and the real world. So if we step back and we say, well, what is optimization? Hopefully the answer to us isn't, it's the search for the best basis on a matrix, right? Hopefully the answer should be, it's the search for a minimum or maximum solution to some problem that I have. And what we can see here is as we talk about what optimization is, typically, if we're communicating that to somebody who isn't in the field, we're talking about it in a way that has nothing to do with mathematics. And I think that's sort of a key point in that optimization itself is not necessarily a mathematical field. It uses a lot of mathematics in different ways, but in and of itself, it is a field that tries to solve problems. And I think of it now as really just a set of strategies. So if you are familiar with the hybrid optimization community, you've probably come across the name John Hooker. He has a wonderful book out called Integrated Methods for Optimization. And what he has done is really look at different technologies that have been applied to solving hard optimization problems, such as mixed integer programming, constraint programming, global search and heuristics and so on and so forth, and found that there are key elements or strategies that can often be abstracted. And the ways that those are applied to particular technologies, like say linear programming, are maybe specific to that technology, but they are still, say, a search or an inference or relaxation procedure. And so, what he has found is that successful applications of optimization technology usually involve these three elements in some way. And so what is search? Really, it's just the enumeration of solutions. I have a problem, I'm going to go search for a solution. And there are different ways to do that. Inference is essentially learning as you explore a space. You might determine that something can never be true in your solution, or you might be able to find a bound and use that to prune parts of the search tree out. And then relaxation is the technology of taking a hard problem that we don't know how to solve and replacing it with something easier that gives you a place to look. And so when we combine these three things, what we typically see is that irrespective of the vehicle, the underlying vehicle, whether that be a matrix or a finite domain set or whatever, we usually see sort of a multiplicative aspect where adding these technologies together gives us more and more power in our optimization. It's particularly interesting to think about this as in the context of Nextmove, because what we are trying to do is get optimization closer to software engineering and remove some of that translation layer. And so typically in an operational environment, I might have data that looks like something on the left. This is just routing data. And if I'm building a software microservice or working directly on operational data as an ops person, I'll be interacting with something like this over on the left. But today, if I want to plug in an optimization solver into this data or to work with this data, I've got this translation procedure that I have to go through. And so there is a question here of, if we change the underlying vehicle of optimization, if we experiment with new things, can we create models that have the same strategies, but can operate on something that is closer to the real world? And I think that's a valuable thing to experiment with. So again, if we think about optimization less as math and more as search strategies or problem-solving strategies, what does that give us? And that will then bring us to decision diagrams. So let's talk about decision diagrams. If you have no exposure to these things, well, actually, first let me start with some acknowledgements. I don't want to give the impression that we invented these things or have pioneered all of this work. There's been a lot of work in decision diagrams actually going back to the 1950s, I believe. They were initially created for circuit verification. And in the last 20 years, people realized that you could restructure a branch and bound and on top of a decision diagram and use it as a vehicle for optimization. So there's, if you look for some of the work that's been coming out of Carnegie Mellon last 15 years or so, you'll find wonderful academic and papers on this and very interesting research. So please go look at what these people are doing. What we are mostly doing at Nextmove is applying these things to solve problems at large scale, along with lots of other things like mixed integer programming and heuristics. So look at what these people are doing. It's really fantastic. All right, so what are decision diagrams? If you have no exposure to these things, the simplest way to think of them is as the search for the best solution along as a shortest path on a graph. And so we'll look at what they look like structurally in a minute. But basically, imagine that you have a bunch of choices to make. I'm going to pack items. I'm going to select between things. I'm going to make assignments, whatever. Those choices can really be anything as long as they're finite domain choices. And you're going to make them in some kind of order. So you layer your choices, go to stop one, go to my second stop, go to my third stop. There's some natural progression to doing these things. And then you put this on a graph. So it's a layered directed multigraph that goes from a source node to a terminal node. And as you traverse that graph, you construct a feasible solution and you accrue cost. Right. So what this essentially does is it turns optimization problems into the search for a minimum or maximum path, the shortest or longest path on a graph. Where do they fit in the world of optimization? Why might I be interested in these things? They're not replacing anything necessarily. If as countless academic papers have found, different solution technologies apply well to different problems. I see decision diagrams from my own experience as sort of solving this middle ground between something like mixed integer programming, which has very strong dual bounding or optimality reasoning capabilities because of its built-in linear programming relaxation, and constraint programming, which is very good at solution generation very quickly. So if you've used a MIP solver, you may have noticed sometimes it spends a little time like trying to add cuts at the root node of your search tree and generate really, really good bounds. If you use a constraint programming solver, you've probably had the experience where you give it the model and all of a sudden it starts generating solutions and just you've got tons of them, but it's not necessarily proving optimality very quickly. Decision diagrams kind of have a mix of both of these capabilities, which I think makes them very nice for real-time optimization, because you need to generate high-quality solutions quickly, and you do want the ability to infer from the search tree and prune out parts of it and things like that. All right, so what does this decision diagram look like? Well, we talked before about how it is a layered directed multigraph. So this is what we call an exact diagram. Imagine that, I'm just going to assume you all can see my mouse. Imagine that I have a source node and a terminal node. And what the diagram does is it essentially has paths that go from the source to the terminal node. And so at each layer, I'm going to make a choice about something. So I make a choice in layer 1, another choice in layer 2, another choice in layer 3. This is a binary decision diagram. Every node has essentially a 0 or 1, 2 choices coming off of it. So it expands by a multiplier of 2 every layer. And at the end of the diagram, I go to my terminal node and I theoretically would accrue arc costs along a path. And so going from here down here to the end represents a feasible solution. And the choices at each layer can really be anything that's in a finite domain. Now, if you're looking at this, you're probably thinking, well, yeah, but this multiplies by 2 at every layer. So obviously this is just a representation of the state space, and it's going to grow enormous as the problem gets bigger and be therefore unsolvable. And you are absolutely right. So we need a way of managing the search, i.e. searching problem restrictions. And so the first technology that's developed within the decision diagram framework is what's called a restricted diagram. And so what this does is it says, I'm only going to search some subset of this tree at a time, or this graph at a time. And what you do is you say, I have a width. So here we have a width of 2. I will only search up to 2 nodes in every layer for each layer. And so if you imagine taking that exact diagram from the last slide and just saying, I'm going to order these nodes somehow. It could be by their value, it could be by a bound, it could be randomly, it just depends. And I will select 2 of them for exploration at every layer, and 2 of them I will defer until later. Put them in a queue, and someday I'll get to them. In a way, this is not all that different from what all other solvers are doing. They are managing states, they are putting them in queues, they are deferring things for exploration at some other time. And so, here what we do is we search this sort of rectangle. I think of decision diagram solvers as searching rectangles, right? So we start at a node, we generate a rectangle. Some of the nodes we save for later. And later what I'll do is I'll go back here and I'll say, well, give me one of these unexplored or deferred nodes, and I'll generate another rectangle, because each one of these things can be the root of a new diagram, right? Since it all goes from top to bottom. And so this is diagram restriction. And eventually I will search the entire tree. But I'm just doing it a little bit at a time, one rectangle at a time. An interesting aspect of this, it's very simple, but I think it's very powerful, is that this gives you, depending on the width, it gives you sort of a balance between depth first search and breadth first search. As I increase the width of the layers or the diagram, I'm approximating a breadth first search. So I get a little bit more diversity. And that's an interesting thing to play with in the decision diagram settings. So that gives us search. How does a decision diagram do inference? And you can probably imagine there's lots of ways you could plug that into a decision diagram. The one that we're using at Nextmove is called diagram reduction or layer reduction. Imagine the best way I can just describe this really just to show it. Imagine that I have an exact diagram that looks like this over on the left. And I've got at my top layer, I've got a blue node and a red node. And below them, everything is exactly the same. I have the same choices that I can make. So what we have here is essentially isomorphisms. And if we can somehow detect that, preferably up at the top of the diagram where the blue and the red are, I can remove them. So let's say that the blue node dominates the red node. I can just leave the blue one in, get rid of reduce the red one out, say they sort of represent the same space, and now I have this reduced diagram. And there are nice aspects to the layering of the decisions that make this powerful and possible within the diagram. So this is an inference technique. There are others, but this is the one that we've been experimenting with and using. And finally, so we have search, we have an inference technology. What is a relaxation technology? Now, in the decision diagram literature, if you look up some of that, what you'll see is most of what it does is construction of these things called relaxation diagrams. And the relaxation diagram is where you essentially generate a layer of nodes, and then you select some of them and you mash them together like mashed potatoes. And the result of that is done through what's called a merge operator, and the result of that has bounds, and it represents an over approximation of the state. It's very similar to the linear programming relaxation mixed integer programming, but it's just done on nodes and arcs, right? We initially had that in our implementations, but we found it a bit unwieldy for sort of general purpose problem solving. It's not always clear what a merge operator should look like. That is sort of applies to many different problems. The area where the implementation we ended up with is what we call expanders. And so very quickly, what that looks like is, imagine we're generating a diagram. I generate this as an exact state. I generate, and then I have these other unexplored states that I haven't yet generated. So these are sitting in my search tree sort of as a single node, which is actually still actively generating nodes. But I haven't created them yet. So I'm not merging, I'm just generating them, things as they're asked for. So this is sort of a lazy way of constructing the diagram. And then as a new node is requested from this expander, it will create a new one, and that part of the search tree will now be explored. So it's similar to the relaxation diagrams. It's just that the relaxation is sort of done a priori instead of after node generation. And we have a blog post on that if you're interested in reading more about it. So what do we use in our decision diagram technology? Again, we don't use relaxation diagrams or merge operators. We use expanders instead, and that is our relaxation. We use reduction as our primary inference technique. And of course, we use restrictors for search. In our routing models, we've also hybridized decision diagrams with adaptive large neighborhood search, which I think is very interesting. And if you install our routing software, you can play with that and see how that works. All right, so let's look at a couple examples. I want to show one of these things in action so that you can see that it works, and sort of we'll go through the progression of adding components to it. We're not going to go into the code because that would have to be a different talk. But let's first look at a couple of different formulations, and these are going to be fairly simple models, but I just want to give you a flavor for, like, okay, I've seen these things, with a bunch of dots or circles. What would it actually look like if I took a problem and tried to solve a problem with one of these things? So we'll look at two formulations. We're not going to look at any math. I promise there wouldn't be math in here. There's not going to be. We're just going to look at the graph representation of these, because I think it's so easy to look at that and then think, well, how would I actually code this? And then we'll solve the sort of naive version of the model. We might just do the knapsack one. We'll do the routing one too if we have a little time. And then we'll add bounds through relaxation, and we'll add a reducer. And what we expect to see is that as we add these technologies to our decision diagram search, that we have a force multiplier in power of the optimization. So let's look first at the 0-1 knapsack model. You're probably all familiar with this already. We're trying to pack items into a knapsack. That knapsack has capacity, items have weight, and the items all have value. So I'm trying to decide what is the best collection of items to bring with me. And of course, this is a well-solved problem, but it's a nice one to show because it's simple, it's easy to reason about, and the diagram looks kind of fun. All right, so we have two different transitions that we can make from or two different decisions that we can make about each item. I could either pack it in my knapsack or I can discard it and not bring it with me. So what I've done here is given the decision to pack an item, the green arrows, and the decision not to pack the item, the red dashed lines, arrows. And I've got three items. So I've got my 3D glasses, and I've got my pants, and I've got my laptop. And I'm trying to decide, well, which of these things do I bring? So each one has a value. Obviously, the 3D glasses are going to be the highest value. And each one has a weight. And the computer should probably be the weightiest of these things. And at this first layer, what I'm trying to decide is, do I bring the 3D glasses with me? At the second layer, I try to decide, should I bring my pants? Do I need them? And the third layer, I try to decide, do I bring my computer? Am I on call? Maybe that decision is made for me. And so what you can see here is, at every step here, we're making this binary choice, and we accrue items or not. And so every possible knapsack state here that is feasible, or that is, I should say, where every decision has been made, is in this bottom layer. Now, some of these will not respect the weight constraint. I haven't done anything on this representation to show that. But if you were actually coding this, what you would do is just constrain that, and the state would not be generated or not added to the search tree if it was invalid according to the weight or if it exceeded the capacity. So this is a very simple representation of this problem, and it's very natural. Order your items and decide whether or not to include them. And the decision diagram solver can handle this quite nicely. Let's look at one that's a little bit more complicated. Here, what I've got is a pickup and delivery TSP. So we have a cat that ordered some ramen noodles, a panda bear that ordered some taco, and a dog that ordered a slice of pizza. And we need to pick up these orders and deliver them. I've got one vehicle, so I need to obviously do my pickups before I go to the deliveries, because I don't want to go to the dog and say, like, oops, I didn't get your pizza. I was going to go there next. Dog would be very angry. And so if we look at, I left a lot of the diagram out because it gets big. But even with just these three pairs, if we look at what the decision diagram looks like, it actually has a very nice operational meaning, i.e. I start wherever my driver is. That's my start location. I go to an end location and I pick something up. I can pick up the ramen, I can pick up the taco, or I can pick up the slice of pizza. From there, I can either deliver my ramen to the cat, or I can pick up the taco or the pizza, right? And if I follow from my source to my terminal node, the variable values that I end up with, the layers, actually specify the order of the route. So this is super nice. Like, there's no translation back from the solution to my operational, to what I would do operationally. It's the same, right? I just follow the path, and that's literally what my driver is doing. And hopefully you can look at this and see how easy it would be to add things like capacity. It's a very natural modeling framework if we think about these things this way. And that there are other ways, of course, to do the branching, to construct the diagram. We have one that inserts nodes that we actually use in production. But this sort of append model is I think very natural and very easy to think about. All right, so let's run this thing real quick. And we'll just do the knapsack one because we are getting short on time. So this is the input data, what the input data for this model looks like. And as you can see, it's just operational data. It's, I've got a bunch of items. Each one has a value and weight, and I have capacity for my knapsack. And that's what all the inputs sort of look like. They just have different numbers of items and different values. So the first thing that I'm going to do is I'm going to run that naive model. So this is just the diagram restriction. And I'm going to give it 11 items, just the input that I showed you. And I'll stream the output and we'll look at the statistics. So if I do that, I can see a bunch of statistics generated by the solver. I've got values. I've got information about the search tree. It generated 110 nodes. It found this solution in the optimal solution in some number of microseconds. And so that's all well and good. So we can literally solve dozens of items in a knapsack now, with this solver. Okay, does it scale up to hundreds of items? Oops, I need to actually give it the right input file. Not really. It's breaking down a bit. Okay, so let's add in the relaxation that we talked about. So I've got another version of this model where it gives me some basic bounds. So what we expect to see is now I should be able to go from dozens of items to hundreds of items. And indeed, I can fully optimize this hundreds of items in this knapsack in milliseconds. So that's great. So does this same model now scale up to thousands of items? Not really. It's still searching. Okay. So let's add the reduction. So now we have this interplay between search, inference, and relaxation that we talked about earlier on. And what I'm hoping to see, I mean, I may have pre-gamed this, but what I'm hoping to see is that, again, every time I add one of these steps, I get this multiplier on the power of my optimization. And so, yes, I do. And that's pretty cool. All right, going back to here, we'll skip the routing model. Does it work? Again, we're not talking benchmarks here, but yeah, as what we find is that the graph structure that we have here and the way we think about it does give us this sort of multiplicative power as we add these technologies to it, and that's what we want. The model that I have ready for the pickup and delivery's capacity to pick up and delivery TSP, and these numbers may not seem big, but this is pretty decent if you're not doing something like branch and cut for fully optimizing, which is finding improving optimality of these problems. So yes, it does work, and yes, we do see some of the same kinds of behaviors that we see in other optimization technologies, and hopefully get a lot of those things for free from Solve. So takeaway from this talk, I do think if we go back to the way the routing model is constructed, especially. I do think it's fair to say that these kinds of formulations may get us a step closer to more natural optimization problem modeling. There's a price to that, of course, which is something like mixed integer programming we've been advancing on for the last 60 years or more, and it is just an astounding vehicle for duality reasoning and optimization. You don't have that here yet, right? Like these things have not been studied that long. And there may be characteristics to them that make certain things impossible or possible. But they are excellent at balancing, I think, characteristics of different technologies between optimality reasoning, feasibility reasoning, time to execution, as well as this sort of natural modeling that make them quite attractive and a good practical problem solver for real-time optimization, which is how we're using it.
Excellent. Thank you so much, Ryan. All right, with the time that we have left here, we're going to take a look at some of the questions that have come in. Don't forget, you can use the chat box, you can use the QA box, which has an anonymous feature, or you can always DM us, whichever you prefer. So let's take a look at what's come in so far. All right, Ryan, our first question is, how do decision diagrams and ANLS work together?
Yeah, that's an interesting one. So some of the members of our decision science team have actually written blog posts about this, so please do look up those too. The short answer is that in our routing software, we're using decision diagrams to sort of manage the search. So we use them as an exact technology, and also to generate initial solutions. So we have a very sort of high-level routing language, or DSL, that you can construct routing problems in. There's lots of different kinds of constraints that you can add to it. The decision diagram part of it tends to be good at finding reasonable, feasible solutions to start from and managing all those constraints. And then once those solutions are found, they get handed off to search threads that are performing adaptive large neighborhood search. And so that's been pretty effective for us. And another part that's cool about this is that the ALNS threads are doing this sort of ruin and recreate procedure. Some of them are able to use the decision diagram code to recreate new solutions. So essentially what you're doing is taking a feasible solution, breaking part of it, and then you hand that back to the original code. And so I think that's kind of a novel and interesting approach to hybridization.
Awesome. Okay, so it looks like we are running up against time. But don't forget, you can always follow up with us on our contact form on our website, which is nextmv.io. We will also be sending you some resources. You may have seen the message in the chat, but you'll be receiving a recording of today. as well as materials. So keep an eye out for that. And then we also hope to see you at our next Tech Talk, which will be routing for package delivery, and that will be airing on March 1st. Check it out. And once again, just thanks for attending today. Take care.
Thank you.